Let's look at the unusual behavior of water. In this area of thermal expansion, we're going to look at the peculiar action that water takes with increasing temperature. Liquids generally increase in volume with increasing temperature and have volume expansion coefficients about 10 times greater than those of solids. And if you've ever been in an area where your pipes froze on your house, or you pulled out your ice cubes and you noticed that the water and the ice swelled up above the height of the ice cube tray, this is what we're talking about here. Water is an exception to this rule over, though, a small range, okay, a small temperature range, and it occurs right around the freezing zone. We can see then in the next graph of the density versus temperature relationship. So as the temperature increases from 0 to 4 degrees Celsius, water contracts, and thus its density increases. Above 4 degrees Celsius, water exhibits then the expected expansion without increasing the temperature. So you can see here from the graph what we've got going on here in terms of density and temperature. Thus, the density of water reaches its maximum value of 1,000 kilograms per cubic meter at 4 degrees Celsius. So that's the magic number there. So the density of water as a function of temperature is shown. The inset at the right shows the maximum density then of water at 4 degrees Celsius. So why does a pond freeze slowly on top and then not so much as you decrease through the depth? Atmospheric temperature drop from 7 degrees to 6 degrees Celsius. We see surface water cool and decreases in volume. The surface water then is more dense than the water below it. The water below has not cooled nor decreased in volume. The surface water then sinks, and warmer water from below then is forced to the surface. This is called upwelling. Macroscopic description of an ideal gas. We need to learn something called Avogadro's number. Avogadro's number is 6.02 times 10 to the 23rd particles per mole. Okay, so we're dealing with particle quantities. The number of moles of a substance then is related to its mass, m, by the expression N is equal to m, the mass, divided by its molar mass. So 1 mole of any substance is that amount of the substance that contains as many particles, atoms, molecules, or particles, as there are in 12 grams of the isotope carbon-12. So we just make a reference and a relationship, and we call that a good relationship that we can count the number of atoms, molecules, or particles. So with that definition, I reiterate it on top here. Carbon-12 has an atomic mass of 12 units, or 12 atomic mass units. 1 atomic mass unit is equal to 1.66 times 10 to the minus 24 grams. So the mass, m, of an Avogadro's number of carbon-12 atoms is given then by the relationship, the mass, m, is equal to N sub A, Avogadro's number, times 12 atomic mass units. So 6.02 times 10 to the 23rd times 12 atomic mass units times the 1 atomic mass unit value, so that's 1.66 times 10 to the minus 23rd grams per unit, gives us 12 grams. So we can see where this mole relationship comes from mathematically. Okay, again, Avogadro's number, given the number of moles in a substance, is related to its mass, m, by the expression we just saw. Then the mass per atom for a given element then is given by the mass per atom, molar mass, divided by Avogadro's number, is equal to N, the number of moles in the gas, divided by Avogadro's number. Okay, these are all values that you're going to need when you do your calculations. Another, something called Boltzmann's constant. Okay, we're going to look at that in terms of the ideal gas. So the relationship says that PV equals nRT, and we can say then that N, as we just saw, is N divided by Avogadro's number, RT. Okay, and these are all values then related to the characteristics then of an ideal gas. So PV then is equal to, let's factor out the N, we have R over Avogadro's number times T, and we say that's equal to N times some constant, K sub B times T. And we can see then that the Boltzmann's constant, that K sub B, then is equal to R over N sub A, which is equal to, in this case, 8.31 joules per mole times K divided by 6.02 times 10 to the 23rd particles per mole. Okay, so we end up with 1.38 times 10 to the 23rd joules per K. So let's look at where this PV-nRT came from and what it deals with. It's something called the ideal gas law. PV equals nRT is a term that has all of the characteristics in this case you can see compressing a gas. The universal gas constant, R, is equal to 8.31 joules per mole times K. Okay, so we end up then relationships that can be either in atmospheres and in liters. Okay, so we have R is equal to 0.0821 liters times atmospheres times mole times K. The volume occupied by 1 mole of an ideal gas at atmospheric pressure and at 0 degrees Celsius or 273 K is 22.4 liters. So 1 liter then, by using the conversion, is equal to 10 to the third cubic centimeters or 10 to the minus third cubic meters. Okay, the best way to learn this and to understand it is by applying it. A beachcomber finds a cork bottle containing a message. The message in the bottle is at atmospheric pressure and a temperature of 30 degrees Celsius. The cork has a cross-sectional area of 2.3 cubic square centimeters. The beachcomber places the bottle over a fire, figuring the increased pressure will push the cork out. At a temperature of 99 degrees Celsius, the cork is ejected from the bottle. What was the pressure in the bottle just before the cork popped? So we start with our before and after relationships. You notice in the numerators, PV nRT final. You notice in the denominator, PV equals nRT initial. So we can solve then by canceling out the R's and T's and the volumes, because the volumes remain constant, the N and R's remain constant. So we're left with then varying pressures on both sides of the relationships, final and initial. So as we move the terms around, because we're solving for what the pressure was final, P final is equal to P initial times the ratio of the temperature final and initial. So P initial, they said, was atmospheric, 1.01 times 10 to the 5th Pascal. The ratios then end up being 372 K over 303 K, which gives us then a value of 1.24 times 10 to the 5th Pascal. Okay, so we converted here our 99 degrees. What force of friction then held the cork in place? Neglect any changes in the volume of the bottle. So we go back and look at something that we learned previously. So we know the sum of all of the forces start off equaling 0, such that the pressure in minus the pressure out times the area minus the friction equals 0. So the force of friction then, we move everything over to the right side of the equation. P in, area, minus P out, area. We can factor out the area out of both of those terms, P in and P out, the pressures. And we end up with a relationship that says that the friction is equal to 1.24 times 10 to the 5th Pascal minus 1.01 times 10 to the 5th Pascal times 2.3 times 10 to the minus 4th meters squared, which is our surface area. So our frictional force then in newtons becomes 5.29 newtons. When we come back, we'll take a look at another example here with a balloon and looking for the volume in the balloon.